Continuing on with class 6 in thermodynamics, we're going to take a look at example 210, and we determine the specific volume of R134A at 100 degrees Celsius, 3 megapascals for the following models. Find them from the charts in the back of the book, treat it as an ideal gas, and then use the generalized chart from figure D.1. This is an excellent exercise, in my opinion, as an engineer. If you can find something in multiple ways, you should. And even when you're just trying to understand something, or you're trying to analyze something, trying to design something, taking a bunch of different approaches and looking at it from different points of view can really give you a lot of insight into what you're doing, and also catch mistakes that you're making. You need to check those things out, and check anything that you're working on out in a bunch of different ways, so to give yourself a sanity check. So let's look them up in the table. Let's see. Well, first off, I should write what the givens are. We're going to look up in, what is this? This is 143. So that is table B5. Okay, so table B.5.1. So you start out with B.5.1, and you look, so it's going to be at, T equals 100 degrees Celsius. We'll find out what our P-sat is going to be. It's just good practice to look at. So we get 100 degrees. Let's see, here's B.5.1, 100 degrees. All the way here at the bottom, you get 3,973. Wee! But we're at like 3. Okay, we're like 3 megapascals. So yeah, we're underneath it. Therefore, it must be a steam, right? So we get 3,973.2. Whoops. 92 kilopascals, and which is so P-sat is greater than P, therefore superheated steam. Okay, so we look up the superheated at 3,000. Boom. We have 3,000, and we look at the specific volume. Specific volume is this column, and we're at 100 degrees, so we are at 0.00665. And we're going to trust that the people who made this knew what they were doing, and say that that is the actual one right there. So from table B.5.2 at T equals 100 degrees Celsius, I should actually say it's the pressure first, because we looked up the pressure first before that. And we had 3,000 kPa. V was equal to 0.00665 cubic meters per kilogram. Now we do it for the ideal gas law. We need to look up for R134A. Let's look up the gas constant. Well, I'm just flipping past it. I'll go ahead and get it later. So from table A5, we come down to 134A, and gas constant is actually 0.08149. 0.08149. This is A5, and R is 0.08149 kilojoules per kilogram degree Kelvin. So if you remember our ideal gas law, PV equals MRT. We want specific volume, so that's going to be V divided by M. So we find this V divided by M. It's going to be RT over P. R, I want to turn this R into thousands right here, so it's going to multiply by, multiply by 1,000, so you're going to get 81.49. That makes that Newton meters per kilogram degree Kelvin. And the temperature is 100 plus 273, or 373 degrees Kelvin, divided by a pressure of 3 e to the 6 newtons per meter squared. Right? This is a megapascal, so it's a million, so that's a pascal. And canceling out the newtons, canceling out the kelvins, and that meter, this meter right here squared comes up and makes that into a meter cubed per kilogram. We're golden. So what we find out is we have 0.010132 cubic meters per kilogram. And now we have two numbers. Let's compare them to each other. If you, so you can take percent right there and just say 1 minus the one that you're comparing, 0.00665, divided by 0.010132. And what you end up with is a 52.4% error. That's not good. That's too much error. So let's see here instead. Let's take a look at the correction factor, if you will, the compressibility factor. First, what we're going to need is the critical constants. So let's see. I'm going to go to table A.2, and let's see, refrigerant R. I know it's on here. I can't find it. Right, there you go. The variant 134A. That's the molecular mass. There's the there right there is the temperature and pressure. And so the temperature is 374.2, and the pressure is 4.06. This is Kelvin, and that's megapascals. So we go, TC is 374 degrees Kelvin. PC is 4.06. So the reduced temperature is going to be, what would we say, 100 degrees, so it's 373. Oh, that's almost exactly 1. Might as well be 1. Approximately 1. Reduced pressure, P over PC, is going to be, that's 3, it's almost 0.75, right? Because that's going to be 3 megapascals divided by 4.06 megapascals, or 0.739, approximately 3/4, right? So let's look this up as best we can. I'm drawing a lot of lines on this. 1, you'll see here's the reduced 1. It comes up right along there. All right, and 3/4, 0.75. All right, so as we've done before, here's 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. So 9, 8, 6. So it's like right in there. right in there. And I think I'm right in here. And that to me looks just over 0.6. According to the book, that was 0.67. So Z is approximately 0.67. If you want to go ahead and check with this guy right here, we went 0.75 here and 0.67. Let's see how close it got. Right in there. That looks about right. Right, you can see that it lands on the 1. Sure. Right, okay. See, this is my little trick. I like to use this thing. Just all you have to do, here I won't do it, is just, all I've done, you can't see it right there. You can kind of see it, right? You can see that I have, there's the picture, right? And I've overlaid it, a graph on top of it with the correct range. I'll nudge it over. They don't always work perfectly because the ones in the book, sometimes they skew. They're not actually, but this one actually worked pretty well. And I can use my just the arrows to try to get this thing on top. But it is a pretty good way to check, I think. I also make the curves. I pick data points on top of that, and I can make equations out of curves. I do that all the time. So anyway, back to this. We know that Z is equal to PV over RT. So we can find V by going ZRT over P. We kind of did all the same thing up above. So what we have is 0.67 times 81.49 times 373 divided by 3E6. And we had a V of 0.006788 cubic meters per kilogram. And if we look up above to our original, that's 0.00665. So if you want to get the percent error, 1 minus 0.006788, that's going to be a larger number, so we're going to get a negative number, is 0.00665. You'll get a minus 2.08% error, which isn't terrible. It's not great, not perfect, but it's better than 52.4%. So really it's just sort of a correction factor we're multiplying it by. There you go. We'll do some more stuff in the next